our skies are capable of unleashing terrible fury. Throughout the seasons, they bring catastrophe in the form of cyclones and torrential rain in the springtime, heat waves in summer, hurricanes in the fall, and snowstorms through the long winter. There is no place on Earth spared these disasters with their devastating consequences. And now, with climate change, these extreme events are growing all the more punishing and more frequent. In the face of these catastrophes, weather forecasters and scientists are swinging into action as meteorology reinvents itself. Never in the history of this science have so many research projects been undertaken and so much technology deployed. Meteorologists are scrutinizing clouds, wind, sea currents, and waves like never before. And as their missions take them from the depths of the ocean to the highest levels in the troposphere, an incredible race against time has begun. The year is punctuated by weather events. Winter brings its storms, and with them, the challenge to meteorologists to predict which coastlines will be hit and what the risk will be to local populations. The lives, safety, well-being, and economic activity of millions depend on their forecasting skills. Today, meteorological monitoring and forecasting are critical for our very existence. But how do we predict the weather? For a long time, the mechanisms determining the weather were a mystery. Until, that is, the invention of the satellite. The launch during the 1990s of the two first satellites in the Met-Op constellation revolutionized this science, allowing us to observe our planet from space.
Before, we only had geostationary satellites at an altitude of 36,000 kilometers, which only show the equatorial regions. With Met-Op, we can travel around the Earth and see it all, including the poles. We are at 840 kilometers, so we're much lower and can take pictures and much more precise measurements.
For its third launch, the Met-Op satellite was transported to Kourou in Guyana to be blasted into space on a Soyuz rocket. And everyone involved in its design and production met up in Darmstadt, Germany to watch.
Space is never easy, and a launch is never relaxing. Anything can happen, good and bad, and we have to be ready for anything.
Satellite launches are rare events. In the EUMETSAT control room, the tension and anxiety among the technicians who will soon be operating Met-Op is palpable.
I always bear in mind on a night like this a quote from Alan Shepard, who was the first American into space. And his quote was, "Dear God, please don't let me fuck up." Don't fuck up.
Attention pour le début de la séquence d'allumage lanceur. Top faille 0-20 secondes. Langage du VKM, allumage triétage à tous les vidéos. Attention au décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top décollage.
It's wonderful to see all the technology behind a satellite launch. And in the end, we benefit because we receive all the data. It just happens. We don't need to think about it. But when you see all the technology behind it, it's absolutely fantastic.
Today, 80% of the data used by weather forecasters comes from satellites. But these instruments, which only see a very small part of the Earth as they move, are still too few and far between. There are only 16 weather satellites in orbit around the planet. And there are also around 60 research satellites that supply information to forecasting centers. Weather forecasting has become a global challenge requiring huge resources. And climate change is only adding to the difficulties. Scientists are continuing their quest for understanding across the globe.
When the ball drops in Times Square, the wind chill could be -4.
I have never felt the cold like I'm feeling it in these last few days.
For the past few years, waves of cold weather have been regularly hitting the US, Europe, and Japan. But what is the reason for these events? According to some scientists, Arctic warming could be the culprit for this shift. Unfortunately, this geographical zone is difficult to access, and it is rare to obtain meteorological data from there. Meteorologists have understood that to improve their forecasting, they need to better represent this region in their modeling. This is the start of an ambitious scientific adventure from Iceland across to Greenland. The campaign, overseen by the World Meteorological Organization, is deploying a level of equipment that has never been used in this region before. The Alliance, a 100-meter-long oceanographic boat, will be home to dozens of scientists from around the world. It has been kitted out with all the latest oceanographical, acoustic, and meteorological technology. For this mission, the British Antarctic Society is using Alpha Zulu, an aircraft specially designed to fly in polar regions. It can measure wind and turbulence, sea temperature, particles in the clouds, and the sunlight filtering through the atmosphere.
I mean, the trouble is, it isn't very windy.
The main goals of the project are to find out more about the climate system in the Iceland and Greenland seas. So this is a region where the atmosphere and the ocean are tightly coupled. They talk to each other. This is an important component of the main ocean circulation and key for climate for Northwest Europe.
There's another very important aspect of this, and that is to help improve the ability to forecast weather. And you know, the Arctic is changing drastically, I mean, incredibly fast, you know, yet it's such a data-poor region. So we need data to understand better how to do things like forecast weather in high latitudes. And I would contend that not only is it data-poor, but in wintertime, it's almost data-barren.
Until recently, few scientific programs have been carried out in this part of the world. The extreme weather here makes observation campaigns particularly challenging, and it is very difficult to set up instruments for measuring. Robert Pickart and Ian Renfrew have had to wait 8 months to begin this project and finally set sail. Right from the start, the realities of the Arctic are having a profound effect on everyone. The long and difficult task of taking measurements and samples begins as they start trying to uncover the mysteries of the Arctic.
Okay, this is the balloon. The wind direction is this direction. We're gonna get it out, open this flap, get it out, walk there, and give it to Chris, and he will let it go.
New tools have been specially developed by the meteorologists. A prototype submarine drone is being launched for the first time. It should measure the marine currents it encounters between the surface of the ocean and a depth of 1,000 meters. Data like this has never before been captured.
Okay, I'm gonna go inside and get on the radio, and I'll let you know when to green plug it.
Okay, you do too.
The Arctic currents the drone will measure are key to our terrestrial mechanisms. They govern the circulation of global ocean currents and thus of our weather. In Nordic seas, the waters cool under the influence of the atmosphere. They become denser and descend into abysses and head towards the equator. As they move south, they mingle with the waters they encounter, heating up and returning to the surface before heading north again. This heat redistribution is crucial for the life of our planet.
So this program is looking at one aspect of that big overturning loop. It's looking at where the water gets dense, where it sinks, and how it gets into that deep current. That's what we're looking for, and that's why we need to be here in winter during the coldest time of the year.
For more than 2 months, the research vessel Alliance and the Alpha Zulu plane will measure the heat exchanges that are produced from the depths of the ocean to the highest levels in the atmosphere. Flight after flight, and from one destination to the next, the meteorologists hope to find an explanation for the key to changes occurring in the Arctic. It will take several weeks of very hard work before the Arctic starts to reveal its secrets. While meteorology researchers take to the field like a new generation of explorers, weather forecasters are simultaneously developing essential new tools, without which no predictions could be made. Since 1975, the European Centre for Medium-Range Weather Forecasts in Reading, UK, has been revolutionizing the world of weather forecasting thanks to its supercomputers.
We have about 20 cabinets here, so 2 times 10 cabinets, and per cabinet we have of the order of 200 compute nodes, altogether roughly 130,000 cores per cluster. So it's a 260,000 core system that we're running here.
how is it possible to predict weather events in a country or region? For the meteorologists in Reading, this involves dividing the globe into segments, like an orange. They have mapped virtual squares, like the holes in a net. Initially, these squares were 210 kilometers across, but a few years later, they were reduced to 125 kilometers and then 62 kilometers. The atmosphere was also divided into columns and then into horizontal layers, like the floors in a skyscraper. The more precise this geographical segmentation becomes, the higher the resolution of the mathematical model, and the better the predictions for each of these little earthly zones.
So if you translate what we do today, like a 9-kilometer forecast, we have 137 levels vertically. 9 kilometers translate to 6.5 million grid points, times 137 levels, times 10 prognostic variables. That translates to something like 9 billion updates of variables every time step we do a calculation. And with our time step, a 10-day forecast takes about 2,000 time steps. So you do these updates of 9 billion parameters 2,000 times. It is crazy, but it's the problem we have to solve.
Nowadays, computers are some of the most important tools used by scientists. The billions of calculations they are able to make helps better quantify interactions between the Earth, the atmosphere, and the oceans. But some phenomena are still not very well measured, which results in lower quality predictions.
One might think that to do weather forecasting, you just have to sample the atmosphere, and the evolution of that atmosphere will be enough. But the atmosphere interacts with everything: the Earth, the oceans, sea ice, and even tiny particles of ozone or aerosols in the atmosphere. And all of that isn't taken into consideration in our models. So we are driving this concept of coupling, of interaction between the different components that we call our Earth system.
For example, clouds are one of the phenomena that are so difficult to understand. They are part of our daily lives, but are one of the main sources of uncertainty in our forecasting models. Clouds produce rain. They give rise to storms, and they travel great distances. But the story of these huge fluffy formations, from their creation to their eventual dissipation, is full of unknowns. In one of the laboratories of Météo France in Toulouse, a team is developing a new kind of laser. These lasers are able to count the number of drops of rain in a cloud and detect their volume and concentration. Cyrielle Dangean is particularly interested in very small particles in suspension in the air, without which there would be no clouds over the Earth, aerosols. These particles, which range from just a few microns to a few millimeters across, allow water vapor to transform into droplets.
Aerosols have many sources. Some are naturally emitted into the atmosphere, such as desert dust from the great deserts around the world. Then there are aerosols that come from the oceans, what we call marine salts. There are also aerosols that come from plants, which are organic aerosols, and then there are other aerosols that stem from human activity.
To better understand the role of aerosols, Cyrielle Dangean has had to find a special place where some very different air masses converge, bringing a range of different aerosols with them. She has decided to set up an aerosol trap in the Pyrenees at more than 2,800 meters above sea level on the summit of the Pic du Midi mountain.
I'm particularly interested in black carbon aerosols that come from pollution linked to human activity.
Black carbon aerosols are really upsetting our climate. Been emitted into the atmosphere since the Industrial Revolution by factories, airplanes, cars, and wood burned for heating. And until now, studies of them have been relatively limited.
We are now interested in these particles because we have realized they may play a critical role in the life cycle of clouds. If that's the case, then this could be very serious because black carbon aerosols come from human activity. And if human emissions increase, there could be an even greater concentration of black carbon in the atmosphere, which in turn could change the quantity of clouds in the atmosphere.
But that's not all. These aerosols also have a secondary effect on the clouds. They warm the Earth by absorbing sunlight. And this hike in temperature encourages the evaporation of water droplets in the clouds.
Because of this absorbency, black carbon is changing the temperature of the atmosphere and playing a key role in the end of life of clouds by making them disappear.
The effects of black carbon aerosols around the planet is still mainly a mystery to us today. Depending on the season, clouds are also responsible for catastrophes. As they develop at the end of the summer, they often trigger storms. And these storms, which are often difficult to predict, sometimes have dramatic consequences.
This bridge in Vilgaillac was unable to withstand the force of the flow. It has been sliced in two, and the emergency services have had to evacuate those affected, like this old lady, helicoptered in the other side of the river for treatment to her injured leg. In the village of Trèbes, entire neighborhoods are underwater. Vehicles have piled up, roads are impassable, and houses are destroyed.
We don't know what we're going to do. It's a disaster.
Why weren't we warned in advance? Why didn't they tell us to seek shelter? 2 million people around the world now live in flood zones and are threatened with the dangers of storms and high water. Storms have become an essential area of study for meteorologists. This year in France, an intrepid team is planning to travel right to the heart of these inhospitable masses. Using the meteorological research plane belonging to Météo France, the CNRS and the CNES, a team of around 30 storm hunters, are planning to study a phenomena that often occurs with storms, lightning. Lightning can happen at speeds of up to 20,000 kilometers per second. And measurements have revealed that the temperature within some of them can reach up to 30,000 degrees Celsius. These figures show what is waiting for Eric Defer and his team.
We want to understand how storms form and how lightning forms. More specifically, how it is triggered and why it is propagated, and why it is propagated over such great distances. Another objective is to look at how data relating to lightning can be assimilated into digital weather forecasting models, and how one day we can use this to improve our forecasting.
The arrival of storm episodes over the Mediterranean is the signal the storm hunters have been waiting for. Preparations for takeoff can begin.
These aren't our normal missions because usually, as pilots, we try to avoid storms, and here, they want us to go inside them. We try to go up as high as possible, above the anvil of the storm cloud, and then the raster radar, which is behind us, can study the vertical composition of the cloud, and in particular its water, snow, ice, and hail content. Our objective is to try to get as close as possible to the storm system, so we then descend through the cloud as low as we can, while ensuring the flight is still safe.
For 5 hours, the plane and its team of scientists pierces the clouds, aiming for the heart of the storm and recording the electric fields that accompany each burst of lightning with the onboard equipment. At 8 p.m., they returned to the base at Solenzara for an immediate debriefing.
There are also things we didn't really understand.
An examination of the images captured by the camera on the plane's nose has a surprise in store for the scientists.
We're wondering if it wasn't us that triggered the lightning.
During the flight, in a fraction of a second, the plane is hit by lightning.
We can see very well here that the plane was flying at 8 kilometers of altitude, and the cloud is developing it up to 12.5 to 13 kilometers of altitude. So we can see that the electric field is increasing as the plane approaches the center of convection activity where the lightning occurs. In the end, for the general public, it's more about very short-term storm forecasting, about where a storm is going to be in 15 or 30 minutes' time, and what shape it will take. The idea behind the Etc. project is about providing additional information to what we already have, to refine the scenario we will be experiencing in the next 15 to 30 minutes.
In a few years' time, and thanks to lightning, meteorologists hope to be able to predict the location and strength of storms. Not just to the nearest half hour, but a day before they occur. Meteorology is a race against the weather. And with the increase of such devastating phenomena, it's becoming more essential than ever.
We came running out. The hurricane was so violent, and it wasn't stopping, so we went outside.
I lost everything, how you can see. And all my neighbors lost everything. It's hard.
Well, life is tough, you know, you can't keep crying, you just have to step up and deal with what you have to deal with, because everybody is feeling it. The rich, the poor, everyone is under the same kind of crisis.
With every new catastrophe, the same questions arise. How can we plan the exact trajectory of hurricanes and predict how intense they will be? These phenomena occur almost every year. Every year since he moved to Martinique, meteorologist Jean-Noël Degrasse has seen a dozen tropical cyclones develop above the Atlantic. Along with his co-workers, he establishes the conditions for their formation off the coast of the African continent. When the ocean temperature goes above 28 degrees Celsius and the humidity intensifies, these turbulent phenomena sometimes turn into cyclones. On August 30th, 2017, Jean-Noël watched his 10th tropical cyclone of the year begin to form. Irma had all the characteristics of a major hurricane. The meteorologists were on the highest possible alert.
Hurricane Irma, rapid intensification, Category 2 hurricane. This will be a very dangerous storm and potentially could affect the Caribbean, the Lesser Antilles, Puerto Rico, Dominican Republic, potentially the East Coast, and the Gulf of Mexico or Florida. That's why we need to pay attention. So, heading into Sunday, Monday...
1 week before he arrived in the West Indies, the European Center for Medium-Range Weather Forecasts in Reading, the NOAA in the USA, and Météo France all confirmed that Irma was going to be big.
At that point, the question was whether it would continue to intensify. And according to our database, since 1950, there has never been a Category 5 hurricane that has hit a small island in the Lesser Antilles. So the message was, we don't want to announce a catastrophe, but this is something quite exceptional.
In the USA, the National Hurricane Center was also monitoring Irma very closely. Its incredible Hurricane Hunter airplane, capable of flying into the center of hurricanes, took off, heading for Irma.
And right now, I understand you're up above this storm, is that right?
Yes, sir. We're located around the eye of the storm, and what we're doing is we're dropping what we call dropsondes, and all of that data gets fed into computer models to help get a better forecast track. One of the things about this storm is not only is it extremely intense in the center, but it's growing in size.
By early September, as predicted by the meteorologists, the diameter of Irma had swelled to an incredible 500 kilometers. The hurricane was classed as Category 5, the highest level, with winds measuring 300 kilometers per hour. It was one of the most powerful ever measured above the Atlantic. Then Irma began to move towards the islands of St. Bartholomew and St. Martin. The red alert was sounded.
On a personal level, and I'd even say on a professional one too, this wasn't something to get excited about. You know, often meteorologists will say, wow, that's an amazing hurricane. Wow, that's okay when it's far away, when it's out at sea. But this one was a few dozen kilometers from an island, and we have friends there. And we've sent people there, willing people, journalists, people to take measurements. We were aware of all that, and so we were wondering if we'd done the right thing, whether we'd put people in danger. We were about to witness a humanitarian catastrophe. That's what we were thinking about at that point.
Despite the accuracy of the weather forecasts given by the models, the consequences of the passage of Hurricane Irma were indeed catastrophic. This hurricane, which also hit the Caribbean and Florida, resulted in 134 deaths, the destruction of thousands of buildings, and cost $65 billion. Monitoring meteorological phenomena, understanding where they will strike, warning populations about the most extreme events. The responsibility of forecasters are many. And when the hurricane season ends, seas that are thousands of kilometers away may also be affected. When there's a perfect storm between wind, currents, and tides, the waves striking coastal areas can have devastating consequences for people, property, and the environment. They can also result in significant coastal erosion. Until recently, a handful of satellites supplied information on oceanic waves using altimeters or radars. But they didn't allow for a detailed image to be built up, nor did they provide precise information about the relationship between the waves and the currents.
Thalia to Brest. Hello.
Yes, it's the Thalia leaving Brest for a mission on the Aeolus Sea. 12 people on board, 3-meter draft, requesting you're okay.
In Brittany, 2 planes belonging to Météo France and the CNRS, and 1 ship from the French oceanographic fleet, the Thalia, have been brought in to help better quantify these ocean phenomena. Fabrice Ardouin is the director of this operation and works out of the Laboratory for Ocean Physics and Satellite Remote Sensing in Brest. His work on developing a way to measure waves on a large scale has resulted in the newly created SKIM project.
We're in the process of developing a new satellite that will measure currents and waves. It uses a Doppler radar, and it's the same principle as when the police use radars to carry out speed controls. But instead of measuring the speed of cars, we're measuring the speed of the surface. And this visible surface speed provides us with information about currents and waves. Using the Doppler effect, we hope that we'll be able to do it by satellite soon.
Before launching a satellite equipped with this radar, its effectiveness has to be proven. The idea is to install it on a plane and compare the measurements taken from the air with those taken by the Thalia on the sea.
We're leaving in 5 or 10 minutes. We'll be in the offshore zone for 1 hour, and then we'll head for Wesson to synchronize with the buoys. They're in position to deploy at midday as planned.
We'll continue with the second one at 20 meters. Pierre, let me know when you're ready. I'm ready, Pierre. I'm putting number 10 in the water.
The yellow buoys we just placed in the water will move up and down with the waves, and we will measure their movement. The same way as when you move your phone and it measures the acceleration. It's the same. We have a system that measures the acceleration in the buoy, and using that we can calculate the height, direction, and period of the waves. Today it's fairly calm, but the swell is quite long, so we'll be able to check that we can measure even the smallest amplitude. We'll check that the quality of the measurements is sufficient, and that will give us better readings when using the plane.
Having a reliable measurement of ocean currents is key, and until now, we haven't had any satellites taking such measurements on a global level, like SKIM can. We've already collected a lot of data that we've never had access to before. They are also experts. They have a lot of confidence, and it's going very well, so I have a lot of confidence in them as well.
Thanks to SKIM, Fabrice and his team will be able to measure not just waves, but also currents that are invisible to the naked eye. On a planetary scale, this promises to be a colossal task. Far from Brest, in the Icelandic Sea, the researchers from the Alliance are also monitoring ocean currents.
Captain, you go to there, and we'll see if we can do a CTD there.
Okay, so now we are crossing here, so we can actually eat directly.
You can actually go head to that one right there.
We will.
Super.
They are trying to understand the weather disturbances that affect Europe and the USA, such as cold snaps, summer heat waves, and floods. They've been gathering data in the sea and in the sky for almost 2 months now. And their efforts have been rewarded. They've just proved the variations in a current we had no idea existed until a few years ago. The northern Icelandic jet stream.
So one of the oceanographic goals is to try and trace the source of that dense water, whether it's coming from the Iceland Sea, whether it's coming from the Greenland Sea. So it's a bit of a puzzle, and it's kind of trying to trace back where that water is coming from.
Until now, in terms of the general circulation of the oceans, scientists had only identified one single cold current in the Denmark Strait, the current that runs along the eastern coast of Greenland. Using temperature, salinity, and speed data gathered by the ship, they've been able to accurately map the path of the northern Icelandic jet stream, a new undersea river. Today, scientists are putting forward the hypothesis that the warming of the Arctic is slowing the flow of this current, which in turn is altering the general circulation in the oceans. These modifications to ocean flows combined with changing air currents might help explain the recurrence of extensive cold periods during wintertime and heat waves in the summer. Traveling to the Arctic, to deserts, or to the middle of the oceans, crossing through our atmosphere, gaining a better understanding of clouds, lightning, waves, and currents. The Earth system is not a simple thing to evaluate. More than any other science, meteorology has now become a collaborative affair across the world because weather events do not respect borders. Every 2 years, representatives from all 22 EU member states come together. Their goal is simple: to anticipate risk and ensure the security of populations.
In the scientific world in general, there is a great deal of cooperation, and in meteorology, there is perhaps even more than elsewhere. We collaborate a great deal with our member states, their meteorological services, but also their universities and institutions. We also work with organizations outside Europe, with the USA, with China, and with many others. It's something that really brings together many of our scientific activities on a global scale.
Major weather research programs are now decided on a European level. This was the case this year with a critically important project called Aeolus, which will study wind, a key parameter for weather forecasting in a way that has never been done before. In Toulouse, scientists have designed a satellite that is capable of measuring wind in the different layers of the atmosphere all around the Earth. Its mission is an audacious one. Aeolus is going to use a very high-energy ultraviolet laser that has never been used before in space. Agencies like NASA have already tried to develop similar systems, without success.
We are going to use the fundamental properties of the laser. Primarily, we'll be using the laser's emission frequency. When the beam strikes particles in the wind, these particles will send back data that we can use so we can work out how fast they're traveling, which will give us a good idea of wind speed. The only problem is that when you put an optical instrument on a rocket, during takeoff, the rocket vibrates and shakes. The impact is like a massive earthquake, and the equipment has to survive that shock. If it shifts by a single centimeter during takeoff, all our measurements will be out. And then there's a second challenge. The sun heats up the sides of the satellite, and there's outer space on the other side, which is at minus 270 degrees. So the sun is roasting one side, and it's minus 270 on the other, and the optical instrument needs to be stabilized at 20 degrees to an accuracy of a few tenths of a degree.
The final problem to resolve is the space radiation that will attack the equipment's lenses. The scientists have had to develop special treatments to protect the laser's lenses against radiation damage. This project has involved years of testing. In total, it required 15 years of work before the satellite was finally ready to launch. August 22nd, 2018 in Darmstadt, Germany. This is a key moment. All space and weather agencies are focused on Kourou, where the launcher is due to take off, and on Darmstadt, from where the satellite will be controlled when it enters orbit.
This is an extremely important moment because any launch can fail, and that would be 20 years of our lives up in smoke. Or it could be a great success, and then it's like a baby being born. It'll be over, we'll have cut the cord, and it'll grow up with us scientists, and that's when we'll see if the mission will bring everything we hope for.
Top, page 0 moins 4 minutes. Top, page 0 moins 1 minute. À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top. Allumage P80 et décollage VV12 Aeolus. La propulsion est nominale.
It has to work. It has to work.
Will Aeolus give us a sign of life? A few minutes after leaving the Earth's surface, the satellite should now be able to communicate with the people that launched it.
Yes, it's communicating. There's a signal. And a second one. It works. It cried. We can see 2 peaks. And those are the first cries of our baby. They look happy. They look very happy.
Soon, observation satellites and ground stations will be transmitting billions of pieces of data every second. The future of weather forecasting is being built in this exponential growth of new equipment, observations, and information. It is thanks to information technology that this race is being won. And yet today, the technical constraints imposed by the laws of physics still seem insurmountable to scientists.
Since our strategic goal is to run 5-kilometer global ensembles in 2025, this translates to an inflation of our computing requirements by at least a factor of 100. So our current system is able to run 8 petaflops. This is 8 times 10 to the power of 15 floating point operations per second. This is a very large number. But if you multiply this by 100, which would be the requirement that we would have to fulfill in 2025, this is basically unaffordable in terms of computing technology that you would have to buy and the electric power to supply it. We really need to invest in different types of thinking.
The future of weather forecasting will involve a technical and scientific evolution, the effects of which we are as yet unable to measure fully. Will forecasters one day manage to totally model our Earth system with its winds, clouds, waves, and currents? Will they soon be able to predict the weather with a resolution of 1 kilometer over 200 levels of atmosphere, 10 days in advance as they hope? Thanks to their research, the satellites of the future, and all the equipment yet to come, meteorologists are on the brink of radically transforming our lives on a daily basis.